Hello everyone. At first, I would like to thank the organizer for giving me the opportunity to present my work. The title of my talk is Functional Characterization of Molten Globule State of Protein based on microscopic simulation. Okay, so now just to say the stage, I just like to two, three word about the molten globule state. It's a very known word in the protein science. Now, specific definition of the molten globule state is a state in which specific tertiary structure is disrupted without loss of the secondary structure. Now, basically, the molten globule state is a intermediate state between the unfolded and folded state. So, in equilibrium, if one want to achieve the molten globule state, we need some mildly denaturing condition like low pH, high temperature, even presence of any like chemical denaturing like urea. Now the question is, so we can, this is a free energy plot landscape, and you can show that molten globule state basically in between state between the native and unfolded. So to capture the molten globule state is not a very easy task. And second question may ask the why we are doing this, why molten globule state is important. So to explore this thing, I consider we consider alpha lactalbumin protein, which is small calcium binding protein which present in mammalians milk and function as a specificity modifier of an enzyme that are galactosyltransferase transferase. Now previous experimental evidence suggests that this alpha lactalbumin protein behave pH dependent way, that is if pH change, its conformation is various property change, activity basically change. Now at low system pH it's formed basically molten globule state. Now at low pH it, and the molten globule state, it bind the oleic acid and basically it shows the cytotoxic activity specifically against a cancer cell. This is called the Zamlet. Well, X is basically human, and then Hamlet. If you consider bovine, then it will be Bamlet, etc. So this is a system. So this is the structure of this is a human alpha lactalbumin. This is a bovine lactalbumin with the calcium ion. This is, you can see that the this is sequence comparison. You can find the most of the sequences same sequence. Similarity is 75.6%. The star marks basically shows the same residue, same amino acid residue. So there are some difference, or there is some difference is present in the case of sequence. Now we use the constant pH molecular dynamic simulation, which is used in the AMBER. Okay, so because conventional simulation did not show you any molten globule state, because maybe protein stuck in the energy minima, so we did the constant pH molecular dynamic simulation with AMBER. We use the AMBER 99 sp force field with the generalized bond implicit model is used as a model solvent. In acidic pH, residue tyrosine and lysine were excluded from the titration, while glutamic and aspartic acid residues were excluded for simulation basic pH. And for at pH 7, that's a neutral pH, we just titrate the histidine because its pK value is nearest the neutral pH. Okay, so what the early experiment says? Early experiment says that for alpha lactalbumin protein in molten globule states, its radius of gyration increase. Anyone experiment had confirmed that at molten globule state that 31 and 32 residue distance between those basically increased significantly in the molten globule state of alpha lactalbumin protein. Third point is that native contact very much reduced at molten globule state at compared to the native step. Okay, so experimentally this is also this group on 1993, this in 81 they show the same thing. Contact basically reduced and non-native contact as a result increased. So these are the most evidence, the popular evidence that shows that prove the presence of molten globule in any case. Okay, so we try to calculate these things using the simulation. So you can find the two panel, this is for human and this is for bovine. This is yellow color is basically for pH 7, and we perform the three simulation at pH 2, 1, 11, that's both acidic and basic. So we find that for bovine lactalbumin that radius of gyration increase, but for human we did not find the same thing. Okay, and when we consider distance between 31 32 and distance between them increase at acidic and basic pH from the native state, that from pH 7 for bovine but not from human. Okay, now we discuss about the native contact also decrease for bovine, and this is this one at both acidic and basic, but non-native contact increase for both acidic and basic pH, but for human we did not find the similar any kind of similar thing. So we find that only the bovine alpha lactalbumin somehow showing the best result. then we discuss about the secondary structure. There was a group on 2019 published a paper on proteins. They show that the beta sheet structure basically decrease at various pH, acidic and basic. They use the canine lysozyme, which are similar characteristics in the molten globule state like the alpha lactalbumin, and we got the similar kind of thing that pH 7 it will be beta structure amount of beta state decrease at pH 2, 1, 11 as compared to pH 7. So as a conclusion, we use the constant pH molecular dynamics as a tool to explore the conformation characteristics of the lactalbumin protein. And secondly, we check the formation of molten globule state at both acidic and basic pH. We find that pH 2 as a best pH to explore further characteristics of the MG states and its cytotoxic activity against cancer cell, and the work is currently basically underway. Okay, so this is my references, and I would like to acknowledge my guide Professor Jaydev Chakraborty, DST for funding, and SNB and CBS for computational facility. Thank you.